So the challenge is fabricating these in order to find out whether or not they're actually going to be successful. So we're going to need thin, large wings that we can actuate at the resonant frequency, and they need to be piezoelectric. Now we don't actually need silicon to be on the other side of it to just test whether they produce the right force when they're flapping big enough. So the easiest first approach was to take quartz, put metals on each side for contacts, and then put down SUA, the UV cured epoxy, which tends to go down in tension to build up the curvature that we wanted, then apply a resonant frequency and get this flapping. Unfortunately, it is actually kind of difficult to get thin X-cut quartz. The thinnest I could get somebody to commercially grind me was 100 microns, and we needed 7 microns. So the challenge was developing a process that would thin this down. RIE turned out to be a good solution for this, but unfortunately, if you just use a classic reactive ion etching recipe, then you'll find that you get a lot of pitting in the quartz. The solution to this was to include a lot of argon to stop this opening up of high index planes and exposing these fast etching surfaces. By including a lot of argon, we stop the micromasking that tends to open these up in the first place and lead to destructive pitting through the quartz. So this is increasing argon concentration in the plasma mix. And finally, you get some curved up wings that are stacks of 7 microns quartz with tiny amounts of metal on each side, about 150 nanometers of gold on each side, and 7 microns of SU8. And you can apply a resonant frequency voltage and find them flapping. That's when they're not flapping, and then flapping once again. So they turn into just a blur. Using high-speed video camera, we're able to look at what this looks like when they're flapping at 1,000 frames per second. And comparing this with the analytical prediction for the model with not flapping and flapping, you see that it actually fits a lot better than just using the low off-resonant prediction of shape, which would be cylindrical arcs. Now, how do we measure the force? Well, this is the same method that Cavendish used to measure force, which is with a torsion bar. So you take a bar suspended from a thin wire and apply a force at one end of it, and this will tend to cause the bar to twist. So by measuring the deformation of the bar with a laser, we're able to find out how much the bar is actually moved, characterize the torsion bar's transfer function, and then consider that when we calculate the measured force. So measuring the force, we come up with numbers in fractions of micronewtons and can compare that with theory. We are also able to optically measure the amplitude by fitting curves to those previous pictures, and electrically measure the current to find out how much power we're dissipating. Another way to find the power dissipation is by the prediction of what amplitude we should get on resonance versus at low frequencies. How does this compare with the theory? Well, we find that the net force tends to more or less agree with what we would predict, and the dissipated power also more or less agrees with what we would predict. So the challenges were that the wings, while they produce the amount of force that it looks like they should produce, still this is not a particular kind of wing which looks like it should produce enough force to lift itself. So we need to build a different kind of wing here. We need to build one that's going to flap bigger and faster. And this is generation 2 of the wings. These are wings made with quartz and molybdenum as the passive layer rather than SU8. Here's a picture of looking at these wings from the side. These ones, because the molybdenum is so thin, molybdenum is only about 1 to 2 microns on here, depending on the run. These are a total of only about 8 microns thick, so that's on the order of 3 to 4 red blood cells. This is an incredibly thin wing, and you can't even see it from the side. There's no camera tricks here. You might say, oh, this is just what the iPhone looks like from the side. It doesn't have the camera resolution. You'll have to take my word for it. When you look at these from the side, they disappear. You just physically can't resolve them from the side. And yet, at this thickness of membrane, it turns out to be quite robust. So this broken wing notwithstanding, you can see that by flattening it out, it's strong enough to lift up this entire wafer. So this is still 104 microns over here. This is only 8 microns of molybdenum and quartz on top of each other. 7 microns quartz, 1 micron of molybdenum. So flapping the new wings at rest and at 20 volts, you can find another similar resonant sweep and find out their force generation versus frequency, demonstrating good resonance and decent force production. Now the future directions are to find out one that's going to be able to lift itself off, because I can show you these plots and I can come up with better looking plots, but it's not going to be that convincing until I can make a YouTube video which has the robots actually lifting off of the table, right? That's what's really going to be impressive. And so here are the next designs that are going to make this possible. We've got wider wings to use up as much of the area for wings on these 1-inch wafers as we have. Interestingly, doing some initial simulations with the wider wings, all the previous ones I had the length 4 times the chord length, so the width. And why? Because that's the way most things in nature are. So if you look at a dragonfly, it's about 4 times as long there as the chord length. Now what happens if we take these robot wings, which have a length that's about equal to the chord length, and compare it? What we find is that the wide cantilever wings only need about 2 times as much power to produce the same force as dragonfly wings, and only about 3 times as much power as fruit fly wings. So somewhat surprisingly, although everything's obvious in hindsight, the wider wings tend to do better. The theory right now is that the narrower wings, while they're flapping up and down, they let too much air escape the sides, and so while they're building up this extra pressure difference, it doesn't work, it doesn't stick around. But the wider wings don't let the air escape the sides, so it's able to keep this net force production. So, summary so far, we've determined the resonant shape, the net force output and dissipated power, created an analytical framework for analyzing active wing robots, fabricated quartz to 7 microns and created active wings that exerted a measurable force, then created a testing to combine optical, electrical, and mechanical characterization to validate the analytical model. Future challenges are going to be depositing layers that have reproducibly high strains to try and get into this 90-degree curvature range, but yet still have low mechanical damping. SU8 had problems with the damping that was produced in this layer, so tends to be more lossy than just a single crystal material, and yet also have good stiffness matching to quartz. This was another problem with SU8. Ideally, we want a Young's modulus around 100 gigapascals, thickness close to 6 microns, and a product of the two close to 600 kilonewtons per meter, even if either one of these is off by a bit. Then measuring force reproducibly is always going to be a challenge. It's very noisy in the lab and hard to measure forces that are this small. Connecting electrical contacts or wires to the tops and bottoms of 7-micron thick membranes is quite challenging right now, and we're working on ways that we might be able to do that. And bonding quartz and silicon at 270 degrees Celsius, which is a gold tin eutectic, might be a next approach in order to get solar cells into silicon and supply 50 volts at 150 hertz to the quartz layer below them, possibly with cascaded cells. And that way we can have, with no wires, this pair of wings or pair of 4 wings actually lifting off a table just by supplying light. And then keeping the robots under control after that. So thank you very much for coming to the talk, and I'd be happy to take questions.